Okay, good morning. Today we're going to observe or study about filters. Basically, a filter is a one which will remove unwanted things. Here in DSP as well, we'll use filters to remove a so-called unwanted things in general in terms of signals or in terms of digital signal processing. We need to remove an unwanted thing, what is known as noise. So in general, we'll use filters to remove unwanted noises so that we'll get the actual signal that is needed for us. Uh, we will see the classification of filters. In general, analog filters has been classified into four different types. One is low pass, one is high pass, third one is band pass, other one is band stop filters. Now we'll see, try to understand what we mean by low pass filter. Low pass filter is one, as the name itself suggests, it will pass all the signals which is within the cutoff limit. Say for example, if I consider this as a cutoff point, it will allow all the frequencies right from 0 till here, and it will limit or it will attenuate or it will cut off all the frequencies which will fall above this. That's what we mean by low pass filter. In general, y-axis represents magnitude, x-axis represents frequency. If you observe here, we have used frequency which is represented by omega. So there are two omegas which we're going to discuss. One is this one, other one I'm going to show you a little later. And this is magnitude. In other words, it is a gain which is given by h of j omega. And the one which you are observing below this is nothing but ideal low pass filter. As you are observing here, you will have a clear-cut transition from passband region to stopband region. And moving on to the next type of filter, which is high-pass filter. In high-pass filter, as the name suggests, if this is my cutoff frequency limit, then your filter will not pass any signal which is having a frequency right from 0 Hertz till this particular point. It will attenuate. In other words, it will attenuate. It won't allow. Whereas it will pass all those frequency signals which will have a magnitude which is more than this. It will allow all the frequencies, and that is what is known as high pass filter. And this is the ideal high pass filter as you are observing here. So this is the cutoff limit. It will attenuate from here till here, all the frequencies. It will attenuate, or the signal which will have frequencies from here till here, it will attenuate, and it will pass all the signals which is having frequency above this particular limit. That is what we mean by high pass filter. Then moving on to the third type of filter, which is band pass. As the name suggests, it will pass certain band. Say for example, from here till here, it will allow all the signals, whereas it will attenuate or it won't pass all the signals which will have a frequency lesser than this magnitude. In other words, it will attenuate or it will stop. Similarly, it will also attenuate all the frequencies which is above this. That is what we mean by band pass filter, and this is the ideal band pass filter representation. And last type of filter, which is band stop filter. Here, as the name suggests, it will stop certain band and it will pass the rest. Here, if you're observing, now if I set the cutoff limits between this and this, in other words, it will stop all the frequencies which will fall within this particular region, whereas it will pass all the signals in this limit and also in this area. That is what we mean by band stop filter, and this is the ideal band stop filter representation. Again, y-axis represents magnitude, x-axis represents frequency. So in general, analog filter specification has been given by this particular magnitude frequency response. We can study the various specifications from this general analog magnitude frequency response. In general, here in this module, what we're going to do is we're going to design filters. If I take, for example, a mobile phone, before you purchase, you will look into its specification, is it not? Definitely. You'll go look into its specifications, like what is the front camera, megapixel it has, what is the back camera, megapixel it has, what is the RAM, what is the ROM. Like this, you will check for its specification. Similarly, even while designing a filter, we should check for the specifications. Those specifications are as listed here. One is passband frequency. We'll try to understand what we mean by passband frequency. As the name suggests, this is again similar to, or actually this is a low pass filter representation. So as I told, in low pass filter, it will allow all the frequencies from here till here, is it not? So since it passes all the frequency signals which will fall between this region and this region, it is known as passband. In other words, it is passing all the frequency signals which will fall within this particular limit, and this area or this band we call it as passband region, and omega p stands for passband frequency. And similarly, we have one more region that is known as stopband region. So, as the name suggests, stopband region is a one in which all the signals which is having a frequency which is more than this will be attenuated, where omega s is known as stopband frequency. So, whatever signal which is having a frequency which is more than omega s will be attenuated. That is what we mean by stopband region. And you can find one more region between passband frequency as well as stopband frequency, and that particular region is known as a transition region. As the name suggests, it will transfer from passband region to stopband region. Now you can observe the two frequency which I am discussing. In general, here I am using this particular omega p or omega s, this omega. In general, we'll use this particular notation for analog filter representations, whereas I'll use this notation to represent digital filters. Corresponding to omega p, we'll have one gain which is known as passband gain, which is generally denoted by kp, which is nothing but passband attenuation or passband gain. I'll discuss about this in detail little later. Now, as of now, if you remember this, it's sufficient. Corresponding to passband frequency, we have one gain, which is this one, which is given by kp. Corresponding to omega s, we'll have one more gain, which is denoted by k suffix s, known as stopband gain. So in general, if you want to design filter, you need minimum of this. They are passband frequency, stopband frequency. Corresponding to passband frequency, we have passband attenuation. Corresponding to stopband frequency, we have stopband attenuations. Hope you have understood till here. The same thing I have written here. Omega p, passband frequency, omega s, stopband frequency. And mathematically, it can be represented like this. That is 1 minus del p magnitude h of j omega less than or equal to 1. That will appear between 0 and omega p. See here, between 0 and omega p, how this signal is varying? It is varying between 1 and 1 minus del p. The same thing, this magnitude is varying between 1 and 1 minus del p. And for all the values of frequency omega which is more than omega s, how it is varying? It is varying between where and where? 0. This is 0 and del s. See here, for all the values of frequency which is more than omega s, see here, above this, it is between 0 and omega s. The same thing I have written here. Magnitude will oscillate between 0 and del s. Hope you have understood till here. We will proceed to the next concept. So in general, as I already mentioned, if you want to design a filter in general, we're going to design a analog filter. Basically, filters can be classified into analog filter, digital filters. uh, even if you want to design digital filter, we don't have techniques wherein we can design digital filters directly. We're going to design analog filters first, and then using suitable transformation, we're going to convert analog filter into digital filter. That is what we will have as per our syllabus. So as I told, in general, we're going to design filters in this particular module. In general, if you want to design a filter, ultimately it can be achieved by obtaining a transfer function. In general, we will have a transfer function either in terms of S or in terms of Z. If the transfer function is in terms of S, it is analog filter. If it is in terms of Z or Z, it is digital filter. So we'll see various techniques that are available to design analog filter, and then we'll check how to convert analog filter into digital filter. Now the first technique, which is Butterworth technique. In Butterworth filter design, so in general, we're going to design low pass filter only. Then using suitable method, we're going to transfer low pass filter either to high pass filter or to band pass filter or to band stop filter. So if you look here, this line, this dotted line represents low pass filter, which is ideal, and you can observe this curve as well. I have written n is equal to 1 here, and for this dotted line, if you observe, I have written ideal filter, and for this I have written n is equal to 15, and for this I have written n is equal to 10. So we'll try to understand what is this. If n is 1, is it matching ideal frequency response? No. Now observe here. For n is equal to 15, is it matching almost same as ideal filter? And n is equal to 10, it is somewhere in between, right? So what I can conclude from this is, basically here n indicates order of a filter. So whereas in module 1 and 2, n is nothing but length of a filter. Here n is order of a filter. Can I conclude it like this? As order increases, the frequency response matches ideal frequency response. I repeat, as order increases, this is the frequency response, magnitude frequency responses, is matching ideal frequency response. Of course, there are certain limitations wherein you can't exceed the order of a filter. So we'll study that in detail little later. I mentioned if you want to design an filter, ultimately it can be achieved with help of designing transfer function. If you want to obtain transfer function, maybe you might have already studied in some other subjects wherein you have obtained transfer function. What we need here is we need the order of a filter. Once you get order of a filter, here as you have observing n, which is either 1, 2, 3, 4, 10, 15, whatever it may be, we can obtain the poles. Once we obtain the poles, we can easily obtain the transfer function, through which we can say that we have designed a desired filter based on the specifications that has been given. Now, magnitude, this gain, magnitude h of j omega in general is given by 1 by 1 plus omega by omega c whole power 2n whole power 1 by 2. Here omega is this frequency. At any point it could be omega c is cutoff frequency somewhere here, whole power 2n whole power 1 by 2. Now the following observations can be made from this particular equation. They are, let me substitute various values of omega, because this is the one which is varying, right? And I'm going to check what is the magnitude I'll get at each and every case. Now to begin with, let omega be the starting value, which is 0. If I substitute omega is equal to 0, what I'll get? It is given by 1 by 1 plus the value of omega right now is 0. 0 by something, omega c is always 0, whole power something 0, 1 plus 0, 1, whole power 1 by 2, 1. So it is nothing but 1 by 1. In other words, can I say magnitude h of j omega when omega is equal to 0, is it equal to 1? The same thing I have written. That is, when omega is equal to 0, magnitude h of j omega is equal to what? 1. Now, shall we observe the same in this diagram? See here, at omega is equal to 0, its magnitude is always equal to 1. Now, shall we take the second case? The second case is when omega is equal to omega c. Here, omega c is nothing but cutoff frequency. Now, let us substitute omega is equal to omega c in this particular equation. Now, if you substitute omega is equal to omega c, what will happen? This omega c will be cancelled out with this. As a result, you will get 1. 1 by 1 is 1 whole power 2 n. Anything power 1 power anything is always equal to 1. So it is 1. So you have 1 more 1. 1 plus 1 is 2. 2 whole power 1 by 2, which is nothing but 1 by root 2. So here, second observation, when omega is equal to omega c, what is the magnitude? H of j omega, it is always equal to 1 by root 2. Shall we observe the same? See here, at omega is equal to omega c, its magnitude is equal to 1 by root 2. Its magnitude is equal to 1 by root 2. Now, shall we check the next case? Third case is, what will happen if I select omega is equal to infinity somewhere here? What is the answer? Obviously, no magnitude, right? It should be 0. So we'll verify the same with help of this particular equation. Now substitute omega is equal to infinity. What do you get? If you substitute omega is equal to infinity, you will get infinity by something. Infinity whole power 2n, infinity. Infinity plus 1, infinity. Whole power 1 by 2, again infinity. So 1 by infinity, it's always 0. So at omega is equal to infinity, any value, it is magnitude is always 0. So this we have already observed, that is when omega is equal to omega c, magnitude h of j omega is equal to 0.707. Now let me apply 20 log on both sides. If you apply 20 log on both sides to this particular equation, which is equation 4, we'll get like this: 20 log magnitude h of j omega is equal to 20 log 1 by root 2 or 0.707. So if you use your calculator, definitely you'll get minus 3 decibels. That is, if you want to represent this in terms of dB, you will get it as minus 3 decibels. In other words, at cutoff frequency, this magnitude will be reduced by minus 3 decibels. That is what is the meaning of it. And the fifth observation is, as n increases, magnitude h of j omega approaches ideal frequency response. That is, as we observed, as we keep on increasing n, it will approaches ideal frequency response. If n is 1, it does not meet ideal frequency response. And the last observation is, h of j omega is monotonically decreasing function. What I mean by that is, you will have a smooth transition. You will have a smooth transition. That is what I mean by h of j omega decreases monotonically. Hope you understood the concepts. Let us stop here. Thank you.